So in the last lesson, we developed this idea that the force on a wire that's carrying current is going to be IL cross B. And I want you to imagine for a second, I've got a wire that's coming straight out of the screen there. The current actually is going into the screen. So you're looking at a cross-sectional view where that orange circle is, so the current going away from you. The north pole of a magnet is above you and the south pole is below you. So therefore the magnetic field runs downward in that particular picture. If I do this, then the force on that, if I do an IL cross B, if the force, the current is going into the screen and the field is pointing downward, my thumb would actually point in the direction off to the left side of the screen. So I have a force that points to the left, and the wire would actually be shoved to the side by this electric field. Or, I'm sorry, this magnetic field. Now, I want to change the game a little bit here. Instead of looking at a wire end on here, I want to imagine for a second that I've got a ring. Maybe it's a wedding ring or something like that, a loop of wire. And it's going to go in a circle, but now I've got the field going across it like this. And somehow or another, I'm going to drive a current around this guy in a counterclockwise fashion. So I've got current going around and around that brown ring there in a counterclockwise way. And I want to look at what the force is on this guy as a whole. Now the problem is the IL cross B is not the same everywhere. First off, the cross product is going to get screwed up by the fact that the angle the current makes with the field is changing everywhere around the circle. And also, what the heck do I mean by length? Well, what I have to do is actually break this wire up into tiny, tiny segments, ds. Because the force is different on different parts of the loop, I have to add up all the little segments of the loop and how much force each one of them has. And I have to do an integral of ds cross b. This is actually a little bit tricky. I mean, literally what we're doing here is what's known as a path integral, and we're going to stick to very simple cases of this, ones that can reduce down to something a lot more mundane. But for now, I want the thing you realize to be that I've got a current, and I'm integrating how much force is created by every little step along the path it takes with respect to the magnetic field B. So let me show you if I can give you a way of working this out. I'm going to blow this guy up, take another look at him. The current's going counterclockwise, and I want to look first at a little segment of current right there at the 3 o'clock position. It's going upward, so it's going against the magnetic field. And what I need to do is figure out what the ds cross b is on this particular little piece. So take the ds cross b and pull that out, and what I note is that's ds times b times the sine of theta, the angle between ds and b. Now remember, ds is just a step along my path here. I'll get to what that really is in a minute. But for now, I want to point out that those two vectors are anti-parallel, so the angle is 180 degrees, and the sine of that is 0. That particular bit of current right there feels no force because of the magnetic field. And this is true whenever I have a current that runs toward or away from the field itself, either parallel or anti-parallel. So if I take this current and wrap it around to the other side of the 9 o'clock position, that little chunk also will not give me any addition to my force here because it is now parallel to the field and also has no force on it. But if I take something that's, say, for instance, perpendicular to the field, go up to the 12 o'clock position here, I've got the current now going straight to the side. It's 90 degrees to the field, so therefore the sine of theta is 1, and this is going to give me the maximum force up here. This force, because of the right-hand rule, is going to be out of the screen. Take your index finger and lay it along that red line, and you curl your fingers down to the black lines, your thumb's pointing out at you. So the force up here is just going to be ds times b. If I wrap this guy around to the bottom, I'm going to have an equal but opposite force. Now it's into the screen because my fingers are pointing the other way, so my thumb goes into the screen. But it's also maximized. And what's going to happen here is everything on the top half is going to point out of the screen of varying magnitudes between 0 and this maximum value, and everything on the bottom half is going to point into the screen of varying magnitudes with this 0 to maximum value. So therefore, the total force on this guy should add up to 0. And we'll see that, in fact, in a second here. But I want to go just a step deeper on this. Let's imagine for a second that I've got some little segment up there that it's just an arbitrary angle phi with respect to the circle. So I can take that particular segment and I can let phi vary from 0 to 2 pi to go all the way around this circle. I'm not actually going to do it that way, but that's the thought process here, is I can take a bunch of little ds's as I go around this circle, and really all I'm doing is stepping the angle as I go around. Well, let me blow this up and look at it a little more carefully. If that angle is phi right there, and ds is the red line and b is the black line, the angle that I have in my cross product, ds cross b equals ds b sine theta, is the angle between the red line and the black line, that angle theta right there. Now I'm going to do a little quick geometry on this. I know that the purple line and the red line are perpendicular to each other because the purple line is the radius of the circle and the red line is the tangent to the circle. So therefore, I can define a new angle alpha right in here, which is just going to be theta minus 90 degrees, or theta is equal to 90 plus alpha. The other thing about alpha is, since I have a little right triangle made in purple down there, phi is going to be the complementary angle to alpha. In other words, alpha is 90 minus phi. And I can put these two guys together to show that theta is 180 degrees minus phi. So phi is going to vary as I go around the circle, but the angle that means that that circle is going to make with respect to the field is going to be 180 minus phi. Now, it just so happens that the sine of 180 minus phi is still just the sine of phi. There's no change there. I will go ahead now and say that ds is going to be r times d phi. We've seen this before, but basically the idea is if the arc length is r times phi, that's the definition of radians after all, then all I'm changing here is phi, so r is a constant, capital R, and I'm going r d phi to trace out this circle. Alright, so let's put this together and see where it gets us. I'm going to take that ds cross b and mold it back into my equation here. And what I've got is, for the top half of the circle, I'm going to go from 0 to pi, integrating sine phi d phi, and my vector is going to point in the z hat direction, which is out of the screen. The I, R, and B are all constant, so I can pull them on through. The integration of the sine of phi just gives me the minus cosine phi. And when I plug in the limits, I get negative 1 and 1 with the negative sign out front. That gives me a total of 2. So 2IRB in the z hat direction is how much the top half of this circle is being pushed toward me right now. The bottom half's a little bit different because I have to redraw my triangle now, and theta and phi have a slightly different relationship. If you look at that, theta is now down below phi, so I have theta equal to negative phi, and when I plug that in, the sine of phi is now negative sine phi instead. So sine theta becomes negative sine phi. My integral now goes from pi, from the 9 o'clock position, to 2 pi, back to the 3 o'clock position. So when I do this integration, negative sine phi gives me cosine phi, 2 pi gives me a cosine is equal to 1, and pi gives me a cosine is equal to negative 1, so I subtract those and I get 2IRB, but now in the negative z hat direction, into the screen. If I add these two guys together, the force on the top is equal and opposite to the force on the bottom. This thing isn't going to feel a total force. It is, however, going to feel a torque, and we're going to come back to this in the next lesson because we'll deal with this in a slightly simpler shape, in a rectangular shape. But as it is, you can look at it right now and say if the top half is being pushed toward you and the bottom half is being pushed away from you, this thing should flip in position there, and that's in fact what will happen if it's allowed to. Now let me do one other thing here. I want to point out that the force on this guy is related to the direction the field goes, and I've got the field going across it and pointed out to you that there's no net force and that it's going to flip. But I want to say what happens if I stick the field through it. So now what I've got is the field pointing at you coming out of the screen, and I'm going to look at that ds cross b again if I have a current that goes counterclockwise. Starting out here at the 3 o'clock position, if the current comes upward there, take your fingers and lay them in that red arrow direction and curl them so they're pointing at you. Your thumb should point to the left side to the right side of the screen. The force on that little segment of wire is outward, away from the center. The same thing's going to happen if I deal with a force, a bit of current down at the 6 o'clock position. The force there will also be outward. And in fact, any position I go on this circle, the force will be outward. Everywhere on this circle, the force is away from the center, and therefore not only is there no net force on this wire, there's also no torque anymore. It doesn't want to flip from this position. Now, there is an outward push on the wire, and if it's something that can blow apart or is flexible, you might have some response there. But if it's a solid, rigid piece of metal, it's just going to stay the shape it is with no net force or no net torque. If I switch the direction of the current, or if I switch the direction of the field, the opposite effect would happen. If the current were flowing clockwise instead, then all those pink arrows would be pointing inward, and I would have a force inward. But again, it would all add up to 0 because I'd have just as much pulling one direction on one side as I do pulling the other direction on the other side.